All right, so we're ready. So a couple of things to do today. First of all, I have posted for you on Moodle. Let's go take a look at it. The second sample midterm. Now, I mentioned a while back that the second midterm is based exclusively on Chapter 8, our discussion about interest rates. And of course, we finished that a while back. We also, at some point, did the Chapter 8 problem set. Let's see. Okay, there it is. Yes, we finished that up sometime last week. Looks like it was the 29th. So now the sample midterm is exclusively, like I said, based on Chapter 8. So I'd like to go over that on Monday. I put it right here, and so we can download it right now and take a quick look at it. And you can see that, like all other sample midterms, there are some short fill-in questions, and they're all, pretty straightforward. They're based on what we've been doing in that chapter. These can all typically be answered with a single sentence or a few words, occasionally a number or possibly a short equation. And then we have our old friends, the boxes, and we also have several word problems, which will be very similar to what will actually happen on the second midterm. So why don't we agree to have this done for next Monday? It won't take you that long. You'll have the whole weekend. And of course, we just really got through doing a lot of these same exact problems on the the Chapter 8 problem set. All right, so yes, so the answers are here if you need them. Let me just quickly take a look. Yeah, so I've typed it all up. And so all the answers are there. So all the explanation is there too. It's not just the answers, all the explanation. If you understand what went on in this Chapter 8 problem set, you'll have no difficulty whatsoever with the sample midterm. And of course, that means you should have no trouble with the midterm itself. All right. So yeah, we totally covered everything here. So you should be in good shape. And so that will be the second midterm. The final will be sometime in, I think, the week of maybe the 13th of May, whatever that week is. Let me just check. We've got a ways to go before the finals. Calendar, May. I looked it up the other day, but I'm starting to forget already what it is sometime, somewhere in this neighborhood. This week of the 10th, I believe. Somewhere in there is when the official final exam week period starts. In fact, if you want, we can go look it up right now. Yeah, there's, okay, it's 2021. According to this, the final exam week is May 13 through 19th. Okay, so right about here. Now, if we finish early, I can certainly post the final exam sooner. If we're in a normal classroom setting, then we're supposed to, of course, take the final exam during that week. But under the circumstances, we can do it earlier if we're finished with all the material. But anyway you look at it, we've got a couple of more, we've got a few weeks left here before we get to the final exam period. So the final exam will not be comprehensive. It'll just be based on chapters 11 and 12, which I'm sure you will find to be quite a relief, because we really have covered a lot of material in this class. And 11 and 12 by themselves are pretty intensive. So that's where we're going. So don't forget, let's just take care of this sample midterm between now and Monday. In the meantime, we're still working on Chapter 11. In fact, we have quite a ways to go. But before we do that, I did find some interesting videos that we can watch, a couple of more that are more for historical interest than math as such. So you'll see why when we get to it. Hold on one second. So here's 11. And what we had been doing was introducing combinatorics. Of course, we spent quite a bit of time with permutations and combinations and arrangements And so what comes after this is our introduction to actual probability theory, where we were talking about the random experiment and outcomes of a random experiment, like rolling a pair of dice. And we were making a distinction between theoretical and empirical probabilities. And we also started to introduce another problem where we had a case where we roll a die twice and we only were focused on evens and odds, and we were trying to calculate the probabilities of different outcomes occurring. Okay, so we also had a quick review of set theory, which we'll need as we go along. And we were ready basically to dive into the actual theories. We're going to be looking at calculating probabilities for what we call events and also for compound events. And so, we've got a ways to go in this chapter, but what I wanted to do was introduce you to a very important historical figure who was one of the really, I guess you could say, one of the first creators of probability theory in the 17th century. And his name was Pascal. You may have heard of him, and he made some very interesting discoveries in spite of the fact that he was not a mathematician. He was actually a priest. And in fact, the only reason he got involved in this probability theory is because a friend of his was a gambler who needed help with trying to understand how the rules of gambling worked. And so Pascal ended up writing a lot of the most important research papers in the early development of probability theory. And he also created one very important result that we'll be looking at more closely in the second video. So because this is kind of interesting as well as useful, I'm going to show you two videos right now. One is basically a biography of Pascal, and the second one is a focus on one of his most important results, which you may have actually seen before. So let's start with the biography of Pascal. And I think you'll agree that it's very interesting. And so hold on one second. There we go. All right, so let's check this out. As always, I'll post this in the chat room. And then let's watch this. All right. So that's the background. Now you know who this guy is. So what we're going to do is focus our attention on not so much as probability theory. We're doing that already. I wanted you to see, though, was this very interesting video about what they described in the video as Pascal's triangle. It's possible you've been introduced to this before, but it's worth checking it out separately, even though it's not really part of probability theory. It's just interesting for its own sake. And so I think you'll agree that it's a very interesting video. So let's check this out. And when it's done, then we can get back to probability theory. Oh, what happened? Oh, there it is. I was staring right at it. All right, here it is. Let's check it out. I guess they're kind of hinting at you that you should become a mathematician and do more research about Pascal's triangle. Wouldn't that be fun? Of course it would. All right. Well, in the meantime, let's get back to where we were in actual probability theory. And so, yeah, if you look at it the right way, I guess, you can use Pascal's triangle to help calculate combinations. Remember, combinations mean the order doesn't matter. So you would use combinations to figure out how many ways to choose 5 basketball players from a group of 12 people. Or in the one example you had, what's the likelihood of having a family with 3 girls and 2 boys? All of those could be calculated with Pascal's triangle. And so it really is the subject of an awful lot of research. Considering how simple it really is, it's really amazing how much information is really packed in there. So anyway, so let's get back to what we were doing. Now, we did go last time through all this wonderful set theory. And so we're defining formally now, based on our sample space, which you recall is a set that contains all the elements that result from a random experiment. Okay, so here we had a case where we're rolling a single die twice, and we're only recording whether it's even or odd. So because of that, instead of 36 possible outcomes like we had in a previous example, here we're looking at a case where there's only 4 possibilities, and each one of them is equally likely to turn up. The set that contains all these possibilities is formally known as the sample space. And all the probabilities that we need are defined in terms of the sample space. Somewhere along the way, too, we also proved why they're equally likely, which you can do by simply writing out all the possible outcomes of rolling the die twice. I believe we did that up here somewhere, and then just go through and count them all. Like if you go back to this chart and you wanted to know what's the probability of getting even followed by even, you could just take the list of possibilities, which we know are all equally likely to start with. And then you could just say, well, let me count the ones where we have an even number followed by another even number. And we could see this one, for example, and this one, and there's a lot of them, of course. Altogether, we discovered when we went through this that there were 9 of them. And so therefore 9 out of 36, or 1/4, is the probability of getting EE, or even followed by even. And we can do the same exercise for even odd, odd even, odd odd. And any way you look at it, all 4 of these are, oh, there it is, equally likely to occur. With that being said, that makes it easier to calculate probabilities based on the sample space. We want to start, though, by formally defining the word event. And an event is nothing but a subset of the sample space. Okay, so remember what a subset is. It's a set that's completely contained within a larger set. So here's one at the bottom, F. If we define F to be the event that at most 1 even number turns up, of course, that means either no evens or 1 even. This is itself a set, and it contains the outcomes EO, OE, and OO. And you can see F is completely contained within S. Therefore, F is a subset of S, and it therefore qualifies as an event. So when you see the word event, what we're talking about here is a subset of the sample space, and it will therefore have its own probability, which we can calculate in one of 2 ways. So what can we do to calculate the probability of F? Well, we've already seen that in a case like this, all of these outcomes are equally likely. The sample space consists of 4 equally likely outcomes. Each one of these, therefore, has a probability of 1/4. So when I look at F, you can see that what I can do is break it up into the probabilities of each individual element of F, which we already know each has individually a probability of 1/4. So when I add them up, I will of course get a probability of 3/4, or 0.75. Okay. Oh, yes. Hold on one second. Oh, that's okay. It happens. You missed a couple of cool videos though. You can, but the list is on Moodle. You can check them out later on. All right. So having said all that, remember, so here, this is easy to do. We can now calculate the probability of F by just counting the probabilities of each of these elements separately and then adding them up. It's very easy in this case. And that, of course, gives us 3/4. There's another approach we could take too, but only in the special case where each of these outcomes is equally likely. In other words, let's go back and revisit our sample space again. It's not always the case that each element in the sample space is equally likely to occur. We just got lucky here, okay? So sometimes the elements in the sample space are not equally likely. In other words, let's go back to our original example with the dice, where we're actually looking at each individual number. And so if you're only interested in the sum that comes out when you roll a pair of dice, you could make the case that the sample space is equal to the numbers 2 through 12. All right, so let me just mention that down here somewhere. Yes, okay, so I just want to throw in here, just as a side note, I'll just throw that right here. Note the elements of a sample space are not always equally likely. For example, when we roll a die twice, and we are interested in all the possible sums, that can occur. The sample space is okay, but we know from the previous examples, based on previous examples, these outcomes are not equally likely. For example, the probability of 2 is only 2 out of 36, while the probability of getting a sum of 7 is 6 out of 36. So I just want to point that out. I don't want you to get the impression that all sample spaces always have all equally likely outcomes. Okay, so just as a side note, and in fact, we'll go back and we'll do some more probabilities with that in a minute. But first, let's get back to this example. So we added up these probabilities, but when the outcomes are equally likely to occur, another option we have is to simply count the number of elements in our set and divide by the number of elements in the sample size, the sample space. So let me just add this too. When the elements in a sample space are equally likely, then we can do the following, and only then though. Okay. So what we're seeing here only works when the elements in our sample space are equally likely to occur. We can just count them. Okay, so here, for example, with F, if you noticed, F has 3 elements, S has 4 elements, so we can just go ahead and calculate 3 out of 4 and come up with our probability of 0.75. And then down here, I once again mentioned, this only applies when all the outcomes in the sample space are equally likely. Okay, so what about this case though? What do we do now? So, you know, let me do this. Let me go back and copy that chart because we're going to need it again. And we'll do a couple of probabilities based on that particular sample space. All right, hold on. I'll just sneak it in here. Okay. I made a mistake here too. Okay, so let's say we're looking at this case. Suppose that in this case, that we are considering the sums of two dies. What is the probability of getting at least 9 when we roll the dice? Okay, so in a case like that, what we have to do is add them all up. And they're not all equal to each other. So we can't just count how many there are. All we can do is this. We can look at our chart and see that the probability of 9 is 4 out of 36. For 10, it's 3 out of 36. For 11, it's 2 out of 36. And for 12, it's 1 out of 36. And so that adds up to 10 out of 36. All right, so that's what would happen in the case where the sample points or the elements of the sample space are not equally likely. What we have to do is add them up separately. So that approach always works, adding them up separately. It's only when they're all equally likely that we just need to count them. So here's another case. Suppose that we had something like this. We're playing a game with a couple of dice that not normal dice, but there are 2 even numbers and 4 odd numbers. So all of a sudden, everything changes. This is no longer the valid probability set of probabilities because we can go through this chart now and say, well, you know, look what happened. All of a sudden, the probability of getting an even number is only 1/3, and the probability of getting an odd number is 2/3. So what this implies is that the probability of getting 2 evens is now not 1/4, but 1/3 times 1/3, which is a 9th. The probability of getting even followed by odd is 1/3 times 2/3, which is 2/9. The probability of getting odd followed by even is 2/9 because it's 2/3 times 1/3. And then finally, the probability of getting 2 consecutive odds is 2/3 times 2/3, which is 4/9. So now they do add up to 1, if you notice. So now, for the same event, the probability of getting at most 1 even, which is EO, OE, and OO, look what's different. We can't just count them and say, well, it's 3 out of 4. That's no longer true. Okay. So we can't simply say 3 out of 4. Instead, we have to calculate each of these separately and add them up. And now with these new dice that we're using, the probability suddenly jumps up to 8 out of 9. All right, so this approach always works. Let's put it that way. You can always calculate a probability by adding up the individual elements in that set, and that will give you the correct probability. It's only when all of them are equally likely to occur that we can just add them up and divide by the elements in the sample space. All right, so I think that part is done. The one thing I did want to point out here, though, is what happens now if we have, instead of 2 rolls of the die, we have 3. Okay, let me just toss that in here as well, just so you can see how that would change our results. Okay, so what if instead of 2 rolls of the die, we had 3? Suppose that we roll a standard die 3 times and are only concerned with whether the die are even, or the rolls, I guess I should say, are even or odd. What is the new sample space? Okay, so in a case like this, the sample space will be a lot larger, as a matter of fact. In fact, all of a sudden, it goes from 4 to 8. Now here, we're still assuming that they're all equally likely to occur because these are the standard die that you see with numbers 1 through 6. So all of a sudden, there's 8 possibilities. If I define the event to be at least 2 evens, then you can see this event contains 4 outcomes: EEE, EEO, EOE, and OEE. And now remember here, they're all equally likely to occur. So it's very simple to calculate this probability. It's 4 out of 8. And that means, of course, 1/2. All right, so it turns out that if you keep repeating an experiment enough times, obviously the sample space keeps getting bigger. So we just have to be careful. We have to understand how big the sample space will get when we repeat our experiment a certain number of times. So just in general, let me just throw in another slide here. For this type of a case, for the die rolling experiment, the number of elements in the sample space doubles every time the die is rolled. So therefore, if I put together a little chart, the following chart, let's do this, shows the number of outcomes, or I should say the number of elements in the sample space that results from rolling the die n times. Okay, so here, let's do this. Now, we'll put together a chart, and we'll see that, of course, some of these are pretty straightforward. Let's see. And again, there's a green. All right, so we'll have number of rolls, and then we'll have number of outcomes. All right, so this will be very straightforward. 1 roll leads to 2 outcomes. 2 rolls is 4. 3 rolls gives us 8. 4 rolls is 16. 5 is 32, et cetera, et cetera. Okay, that's how that works. Okay, so that way, if you encounter a situation where there's 4 rolls, there would be 16 outcomes. And if you had in the sample space, let's add that in there, and it would go up to 32, and it just keeps doubling every time. Now, of course, after a while, it starts to get very awkward to deal with such large sample spaces, but the number is important because that will help us determine the probabilities. All right. So now with all that being done, now in many cases, we're not so much interested in calculating probabilities of single events. Like we've seen already how to calculate the probability of this F. In one case, when all the sample elements are equally likely, and in another case where they're not all equally likely. But what if we need more complex types of probabilities? So we've created 3 rules of probability to help us deal with more sophisticated situations where we may be interested in knowing the probability of 2 different events taking place. So you can see there are 3 of them. And they're the addition rule, the complement rule, and the multiplication rule. All right, so what are these all about? Now, this is where the set theory gets involved. You'll see pretty quickly why we went through the trouble of reviewing set theory, because we'll need it in these cases. Okay, so we'll start with the addition rule. Now, the addition rule tells us how to calculate the probability that a union of events takes place. So this is meant to reflect the case of unions of events. So here's the formal rule. For any 2 events A and B, the probability of A union B, so remember this symbol is union. And in English, you can think of this as or. And so what we have to do is take the probability of A by itself plus the probability of B by itself and subtract off the probability of both of them happening at the same time. All right, so that's our addition rule. Now, there's a reason why this has to happen. You might say, well, why don't we just add them together? And the reason for that is because if we do, we'll end up counting something twice, which we don't want to do. Okay, so I'll tell you what, first let's go through the rule and then I'll show you why we have to do this subtraction. All right, so imagine the following situation. Referring back to the die rolling experiment, okay, let me just remind you that S equals EE, EO, OE, and OO. Each is equally likely. And so we define the following 2 events. The first roll is even, which means EE and EO. And then down here, we have exactly 1 roll is odd, which means we could have OE or EO. So these both qualify as events. You can see A and B are events. Because A is a subset of S and B is also a subset of S. Now, the question becomes, what is the probability that A or B is true? Not just A, not just B, but A or B. That's what we're trying to find out. I want to know what's the likelihood. Suppose I'm playing some game where I get a prize if either A is true or B is true. What's the probability of this happening? All right, that's a good question. Now, the fact that it contains the word or indicates that we'll use the union to represent this. So this is actually equivalent to saying, what's the probability of A union B? That's what this question really means. Now, we already know that A equals, We have them right here. I've listed all of these outcomes or events. And so, because the sample space contains elements that are equally likely, this means that the probability of A is 2 out of 4, which is a half. The probability of B is 2 out of 4, which is a half. And then the probability of this intersection is a quarter. Or actually, 1 out of quarter. We'll just leave it like that. So applying the rule is easy. Very easy. Because all I have to do now is plug them in and we'll get a result. Actually, let me leave this there for a second for you to catch up. Then all we're going to do is throw them in. All right, so here we go. Here's the rule. We'll just plug everything in. And we have 3/4. And we're done. And that was easy. Now, let's demonstrate why this is true, though. What we'd like to do to prove that this is actually true is we'll sit down and let me just quickly remind you that A contains the elements EE and EO. Let's write that here. Whereas B contains OE and EO. So if I were to actually write out the union of these two sets, I would have EE, EO, and OE. And because, again, the sample space has all equally likely events in it, or outcomes, I can just count this, and you can see I've got 3 out of 4. So I've basically proven that our results are correct. But what we still want to know is why was it necessary to subtract the intersection when we calculated our result? Okay, hold on one second. All right, here we go. So what I'm going to do is use a Venn diagram to do this. All right, so you might recall a Venn diagram is designed to show sets. So here's our sample space. Now the points that we have are, let's see, EO, EE, OE, and OO. It's down here somewhere. So this is A. And this is B. So what do you notice between them? This section in the middle, by the way, is the intersection. So when I use the rule, What's happening here is that if I were to just calculate the probability of A plus B, I'll tell you what, let's do this. Let me call this section, which is just A, but not A and B. We'll call this section 1. This will be section 2. And this is section 3. Now, clearly the union is the sum of all three of these. But if you look up here, if I were to combine, hold on one second, those two events, that would be 1 plus 2. This would be by itself 2 plus 3. Without subtracting this intersection, I'm counting section 2 twice. So therefore, I subtracted it at the end. And when you add these up, you do in fact wind up with exactly 1 plus 2 plus 3. So in other words, right here, you can see why this rule is set up the way it is, why it's necessary to subtract that intersection when we calculate the value or the probability of a union. That's the logic behind it. All right. Now, what about, now there's a special case though. If you look at this carefully, you'll see, you might wonder, well, what happens in the special event that A and B have no elements in common? What happens then? So we have then a separate special version of this rule, which is sometimes called the simplified addition rule. But it only applies when the two sets do not overlap. So with a Venn diagram, what would that look like? It means that, well, we have A and B, but they have nothing in common. And so therefore, that subtraction actually proves to be unnecessary. So let's say this is our Venn diagram. So what's interesting about this is that A and B are said to be mutually exclusive, or sometimes disjoint. That's another word that means the same thing. And the key here is that A intersect B is the empty set. And that implies that that probability is 0. All right, so when that happens, you can see what's the addition rule is going to be a little bit simpler. In other words, instead of this, hold on, equals the sum of these two terms minus the intersection. This is now 0, so we don't need it any longer, and this becomes the simplified addition rule. Now, that doesn't mean if you use the original rule, you'll be fine because you'll just get a 0 here, but it's good to know that there's a separate version here where it really only applies when the two events are mutually exclusive. We don't have to worry about double counting that intersection because there isn't one. All right, so let's take a quick look at an example of this. How about this? Now, this is the same one we had earlier. This is the die rolling experiment with every element being equally likely to occur. So A is the event that the first roll is even, and B is the event that the first roll is odd. Okay, so what happens if we're interested in knowing the probability of A union B? Well, these are the two events. Now, of course, you can see that the probability of A is 1/2 or 2/4 because it has two elements. The same thing with B. So the question becomes, what's the probability of getting A or B? So clearly, this is the job for the addition rule, but if you notice something interesting, A and B have no elements in common. Okay. So what's the probability that the first roll is even or odd? Now, clearly, when you write it that way, you can see that they're not likely, they cannot both happen at the same time. So therefore, we're going to use the simplified addition rule. Note, we don't have to worry about the intersections, and we just add them up and we get 1. End of story. Now, another option we had was this. This is always true with these types of situations. We could have just said, well, listen, in addition, or besides using this rule, all we could have done is this, and it would have worked just as well. We could have noted that as an alternative, we note that A union B, and remember, let me just quickly write this down again. A was EE and EO, and B is OE and OO. Therefore, A union B is a set that contains all these elements: EE, EO, OE, OO. And because they're all equally likely, this probability is 4 out of 4, which is 1. So there you go. Now, there's yet another thing we could have done here, although this is not, doesn't happen very often. Also note that this union is the entire sample space, which implies the probability has to be 1. Because the probability, as you recall from the axioms, is that that probability is equal to 1. All right. Now, so that's pretty much everything we need to say about the addition rule. What about the complement rule? Rule number 2 is the complement rule. Now, before we define the complement rule, what we need to do is figure out what the word complement actually means in this context. Now, the word complement can mean a lot of things. In practice, you might recall if you've ever had, let me just throw this in here. So complements, the word complement can have many meanings. For example, in economics, goods that are complements are consumed together. For example, ketchup and French fries, spaghetti and meatballs, etc. In geometry, angles that are complements. I think that's how it works. I better double check this. It's been so long. Complementary angles add up to 90. Okay, I wasn't positive. Have a sum. Remember that of 90 degrees? Yes, that's right. Complements are 90. Supplements are 180. All right, but here we have a very specific, precise definition for events that are complements. But the key to the whole thing is that they go together somehow. So you have to think about it as they somehow belong together. Just like here with the foods and all the rest in economics and the angles in geometry. In probability theory, two events are complements when the following two things are true. If their union is the entire sample space, and yet they're mutually exclusive, then we can say that A and B are complements. All right, so what I'm going to do right now is give you some examples so that you can get the sense of what this actually means in practice. All right, so we have this formal definition, and two events are said to be complements if and only if both of these are true. So what does that actually mean in the real world? Examples. How about this one? The red and black cards in a deck. Why are they complements? Because, okay, two things are true. All cards are either red or black. Now, keep in mind here, with a deck of cards, the deck is the sample space, i.e. the union of the set of all red cards and the set of all black cards is the entire deck, which is the sample space. So that's why that's true. And in addition, that's not enough though. No card can be both red and black. In other words, red cards and black cards, or I should say the set of red cards and the set of black cards are mutually exclusive. Okay, so in other words, that's why we can treat these as complements. Red, black. All the cards have to be one or the other, but there's no card that can be both. All right, hopefully that makes sense to everyone. You can see the logic behind what this means. So based on similar logic, the following sets are also complements. How about this one? The white and black pieces on a chessboard. The odd and even numbers in the set of all natural numbers. Okay, so again, the idea is that you've got two distinctive sets that cover all the possibilities, and yet they are mutually exclusive. So it's starting to make sense, isn't it? Yes, because you've had to have experienced at least one of these. Even if you've never played chess in your life, you know that the board has white and black pieces. That's all they have. Now, let's also look at a case that is not doesn't qualify. On the other hand, the set of all diamonds in a deck of cards and the set of all hearts in a deck of cards are not complements. Although they are mutually exclusive sets, there are cards in the deck that are neither diamonds nor hearts. And that, of course, means the spades and the clubs. Okay, so therefore, we say that they're not complements. All right, they don't cover all the cards. All right, so unlike red and black, which covers all the possibilities, here we're leaving out half the deck. So these two sets do not form complements of each other. So anyway, with all that being said, we can now formally define the complement rule. But before we do that, I want to note that as a point of notation, in this book at least, we're going to use the symbol A with a little c next to it. Which means a complement, okay? In fact, let me just write it like this. AC represents, hold on. All right, this is better. A complement. Okay, so A with a little c is now going to represent a complement. Okay, now the rule tells us that one of two things, well, two things are actually true, but they both actually represent the same information. We can make the following case that A complement, let me write it like this, the probability of A complement is 1 minus the probability of A, and equivalently, the probability of A equals 1 minus the probability of A complement. So the rule is easy, and we're going to apply it in a minute. I also would like you to see why this is true. All right, so first let's do an example, and then I'll show you why this rule works. Let's go back to the die rolling experiment. All right, so we have S equals, once again, EE, EO, OE, and OO. And of course, all elements are equally likely in this case. So the second roll is even. That would be this case. EE, OE. And here we have the second roll is odd. EO, OO. Anyway, so here's what we'd like to know. Let's see, are A and B complements, and why? So are A and B complements? All right, so let's find out. So remember, A is EE. I'll just type this, I guess. So just as a quick refresher, A equals EE and OE. Well, B equals EO and OO. So we need to know two things. What's the union? Whoops, sorry, EE. EE, OE, EO, and OO. And that is indeed the entire sample space. And secondly, A intersect B is the empty set. And so therefore the answer is yes. Both requirements have been met. A and B are considered to be complements of each other, which means if we need to do so, we can apply the complement rule. And therefore, it must be true that the probability of A equals 1 minus the probability of B, and the probability of B equals 1 minus the probability of A. Is that true? Well, let's find out in the next slide. Also, we can rewrite B as a complement. Now that we've proven that they're complements. And right now, all we want to do is demonstrate. Then I'll show you another example. And then finally, I'll show you why this is true. All right, so we already know, because of the way the sample space is constructed, the probability of A and B are equal to 1/2. Okay, and again, it's because A equals E and OE, while B equals EO and OO. So individually, each one of these has a probability of 1/2. Oh, and this is, of course, a complement. So therefore, both of these have to be true. The probability of A equals 1 minus the probability of A complement, and vice versa. Okay, so now here's one. Let's try another one. So suppose we have a situation where the entire sample space is the deck of cards. A will be the royal cards. So you have to imagine the situation is taking place. Let me actually put this in here. A card is chosen from a deck. Okay. That's the experiment. S is the standard, the entire set of cards. A is the event that the card is a royal card. Now, I don't actually think there's a word or name for the rest of the cards. Hold on one second. What is the name of the cards in a deck that are not royal cards? I don't think there is a name for them. Okay, maybe not. I'll tell you what. I'll call them. I don't think it would be nice to call them the peasants. We'll call them the non-royal cards. How about that? The card is a non-royal card. All right. Although I guess they are peasants. They're non-royalties. So if I wanted to know what is the probability of A, Well, what you could do is something like this. You would note that each card is equally likely to be chosen. Okay, A contains 13 cards, not 13, 12 cards, while B contains the rest, 40 cards. Okay, so therefore, if I wanted to know the probability of A, I could actually calculate it as 1 minus the probability of B, which is 1 minus 40 out of 52, or 12 out of 52. Now, you might say, well, why don't I just calculate it directly? Sometimes we may not have enough information to calculate it directly. So sometimes it's easier to use the complement rule than to calculate a probability directly. Okay, now here's what I want to show you. Why, how is the complement rule derived? Okay, just so you can see where this thing comes from. Because I think that'll help you understand what it's for and how it works. What is it used for? All right, so we have two sets. A and A complement. So for two, we already know that for two events to be complements, two things must be true. Their intersection is empty. And their union is the entire sample space. So let's say that that's true for A and B. Okay, so assume that A and B are mutually exclusive and that their union is the entire is the sample space. Okay, then applying the addition rule, it must be the case that we know that they're mutually exclusive so we don't, so in other words, we can subtract 0 so this part is true. We know that based on the addition rule, the union of the two must be the sum of the individual probabilities. But in addition to that, we know one more thing that's very important. Since since A and B, or I should say the union of A and B is the entire sample space, then it must be true that, okay, so we already know that that implies that the probability of A union B is 1. So therefore, based on the last set of slides right here, therefore, since you already know that this equals A plus B here, and that tells me that the probability of A is 1 minus the probability of B, and the probability of B is 1 minus the probability of A. So in other words, based on our assumption that these properties are true, And that plus the union, the addition rule rather, implies the complement rule. In other words, it's derived directly from the addition rule for mutually exclusive events. And that's where it comes from. All right, so now you know what that's all about. Now, the next rule that we see here is the multiplication rule. Now, we saved this for last because it is very, very complicated. In fact, it is so complicated that it requires us to introduce 3 new different types of probabilities before we can define it properly. So because this is such a messy process and because it's Thursday, I think that we've had plenty for one day and we can stop right here. But I would remind you that between now and Monday, I would like you to work on this sample midterm number 2 and have it ready by Monday so we can get through this. And then if there's any time left, we'll pick it up with our multiplication rule. All right. Does that sound like a plan? Good. All right. So then I'll just see you all, unless there's, oh, wait, last minute questions. Yes. Okay. So I'll see you all next Monday then.
Bye. Have a nice weekend.
All right. Bye.